Hello, my name is Andrew Hamilton at the University of Colorado Boulder. You are looking at a black hole. It is being rendered using the Black Hole Flight Simulator. The Black Hole Flight Simulator does full-screen general relativistic visualization in real time. I find it very useful to use this tool in teaching relativity to students at the University of Colorado. You can see that the gravity of the black hole lenses the view behind it. Let's go find an object to lens. Let's find something around here. Okay. There you go. There's a good thing to lens. That's the Andromeda galaxy. This is its primary image, and if you look over here, you can see a secondary image. That secondary image is from light that has gone around the black hole more than 180 degrees. If I position Andromeda exactly behind the black hole, it will form an Einstein ring. Again, the black hole bends light around it so that even though Andromeda is behind the black hole, it appears to form an image around the black hole. Let me bring up a map. The white dot is us in a green regime, which in a moment I'll explain is a regime of stable circular orbits. The black hole is the red thing on the map. It's not to scale. The red line is the event horizon. At the end of this talk, I will take you through the event horizon down to the singularity, and let's have a look at what it looks like. I'll bring up a clock. Right now, the clock is not moving. The Black Hole Flight Simulator is not in flight mode. Let me start the clock. Now, we're in circular orbit around this black hole. Not much seems to be going on. The clock is going by at 1 second per second. It's a fact of life that time always goes by at 1 second per second. You can move this way and that in space, but in time, it's just one direction forward at 1 second per second. Would it be nice to be able to go forwards or backwards in time? Why is that true? I don't know. It's just a law of nature. Now, the timing of this clock is appropriate for a black hole whose mass equals that of the black hole at the center of our galaxy, Sagittarius A star, which is a mass of 4 million times the mass of our sun. So we're in orbit around Sagittarius A star. Nothing much seems to be happening. So let me speed up the clock. Again, this wouldn't happen in reality. In reality, you can't speed up clocks, but in a black hole flight simulator, you can do exactly that. The orbit we're in is a stable circular orbit. It's stable in the sense that if we do a little fire on our thruster, like that, then we will go into an elliptical orbit. You speed it up so that you can see that indeed we're in an elliptical orbit. It's stable in the sense that we're going forwards and backwards in radial distance from the black hole, but we don't fly off to infinity and we don't fall into the black hole. It's an interesting fact that it's only in 4 space-time dimensions that stable circular orbits exist. In 2 or 3 dimensions, there are no bound orbits. And in 5 or more dimensions, bound orbits fall directly into the object you're orbiting. So it's only in 4 space-time dimensions that planets in orbit around stars, solar systems, and galaxies can exist. It's only in 4 space-time dimensions that life can exist. Let me try firing a probe into the black hole. I'll slow it down. I will fire a probe directly into the black hole. Let's do that. Let's slow it down. Actually, let me bring it to a halt. I'll let it keep rotating. But I brought its motion to a halt. You can see the clock stopped. This is a cube. I know it's a cube because I programmed it to be a cube. It seems to be flexing. Why is it flexing? Is it because of the tidal force? No, it's a special relativistic effect. Notice that the side on the right that's going away from us is tinted red. It's redshifted, it's Doppler shifted. And the side on the left that's coming towards us is slightly bluish. It's blue shifted, is coming towards us. Now, the Doppler shift is a Newtonian idea, but this is a special relativistic Doppler shift going on. In relativity, photons are good clocks, so lower frequency means slowed down, and higher frequency, blue shifted, means speeded up, and indeed the side of the cube that's going away is slowed down, and the side that's coming towards us is speeded up. Why does it appear flexing? It's because the light travel time from the far side of the cube is longer than the light travel time from the near side. So we see the far side as it used to be compared to the near side. So it gives the impression of flexing. It's a special relativistic effect. Let's send the probe on into the black hole, and I'll speed it up, see what happens. You can play a game. Will it fall in or not? It doesn't fall in. Why doesn't it fall in? It's because I fired it forwards and I gave it extra extra angular momentum, which gives it extra centrifugal force. And so it doesn't fall into the black hole. In order to get a probe to fall into a black hole, I have to give it a small enough angular momentum. And that means I have to fire the probe in the direction kind of where the black hole is going, down here. That'll give it less angular momentum. Let's fire a whole bunch of probes and see if any of them manage to fall in. Sometimes my aim is okay. Sometimes it's not so good. Let's speed it up so that I can watch this flock of geese, flock of probes falling in, and see if any of them manage to make it into the black hole. Black holes, you can see, do not suck. Yes, you can see from the map at left that we had at least a couple of successes. The edge of the yellow regime is the innermost stable circular orbit. Well, I could try some more probes, but you can see it's tough to get them in. Instead, let's go on into an unstable circular orbit. I'm going to stop it right here. If we were in a stable circular orbit, it looks like that. But if I switch to an unstable orbit using a little button press, there it is, the scene appears to change. Go back to stable, back to unstable. The scene appears to change. It's one of the features of special relativistic aberration. I'm going to be talking more about that aberration. Meanwhile, let's pile into the black hole. Let's start going into flight mode again. We will go into an unstable circular orbit around the black hole. In the map, the region of unstable circular orbits is colored yellow. The green regime is the region of stable circular orbits. It's only in general relativity that unstable orbits exist. They don't exist in Newtonian gravity. Unstable means that if we fire on our thrusters, we will either go off to infinity or we will fall into the black hole. We will not oscillate backwards and forwards as it does on a stable orbit. Let me fire a probe. I'm closer, so maybe my aim gets better. I'm going to fire a probe into the black hole. And let's see, is it going to fall in or not? Speed it up. And the answer is no, it doesn't fall in. I fired it forward, so I gave it extra angular momentum, and the extra centrifugal force sends it away from the black hole. As I'm looking around, I'm actually turning around to looking backwards at the trail where we've come from, there's that probe. If I look backwards, I see the scene as redshifted and expanded, whereas if I look at the forward direction, it's blue shifted and contracted. This is a feature of special relativistic aberration. I'll show more of that to you in a moment. Meanwhile, let's try firing some probes in, and in order to get them to fall in, I have to give them less angular momentum, so I need to fire them to the reverse. Let's fire a bunch of them. See if some of these things manage to fall in. Surely I can't miss at this distance. And indeed, I'm going to declare success. As the probes fall in, you see them slow down and redshift and dim to blackness. Maybe these will fall in. Now, in reality, they would dim to blackness rather quickly. There's another one. But let's brighten up the texture so that you can see that they fall in. There they are. In reality, they would redshift to and dim to blackness, but we see them frozen on the horizon, and they never fall through the horizon. At least they don't appear to from the point of view of us outside the horizon. Why does this happen? This is a mathematically correct representation of a Schwarzschild black hole, the simplest kind of black hole, a spherical black hole discovered by Karl Schwarzschild, director of the Potsdam Observatory in Berlin, discovered by him in 1915 at essentially the same time that Einstein was presenting to the Prussian Academy his final version of his theory of general relativity. Sadly, Schwarzschild, who was serving on the Prussian front at that time, having volunteered to serve his country, became ill with a skin disease on the front. He came back to Berlin and died in May 1916, just a few months after having discovered what we would nowadays call a black hole. So really, we don't know what might have happened if he had survived. The model that you're looking at is a version of the geometry discovered independently in 1921 by Alvar Gullstrand and Paul Painleve. Tell you a little bit about Alvar Gullstrand and Paul Painleve. Alvar Gullstrand was a Nobel Prize winner, won the Nobel Prize in 1911 for his work on the optics of the human eye. And Paul Painleve was another character. He was Prime Minister of France twice, and at the same time as being a mathematician. And both of them independently discovered this description of a Schwarzschild black hole. In this description, space, represented by these blue infalling arrows, falls into the black hole. It falls in at less than the speed of light outside the black hole, hits the speed of light at the horizon, and then falls faster than light inside the horizon, eventually hitting the central singularity. So that's why a black hole is black. Space is falling faster than the speed of light, carrying everything with it. Light that's emitted from inside the horizon, pointed outwards, gets dragged inwards by the faster than light flow of space. A photon which is emitted exactly at the horizon, going outwards at the horizon, just hangs at the horizon forever, going outwards at the speed of light to space that is falling at the speed of light. So the reason stuff appears redshifted at the horizon and frozen at the horizon is not because it stops at the horizon, it's still falling through, but rather that it takes an infinite amount of time for light to lift off the horizon and make its way to the outside world. There's another way of looking at this, which was looked at by J. Robert Oppenheimer and his student Hartland Snyder in 1939. They were wondering what would happen if a star could collapse to a black hole. For simplicity, they imagined a pressureless star. They removed the pressure that would otherwise hold up the star against its own gravity, and they allowed the star to go into free fall. I'm representing it here by a transparent star, so you could see in. It's got an outer layer, and then a layer halfway through, and then the point at the center. Let's watch it collapse to a black hole, see what happens. As the star collapses, it appears to freeze and redshift at what appears to be its horizon. Why is that so? It's because light cannot escape from within the horizon. Light that gets, the last light that can escape is from the horizon. Let's look at this from another perspective. Suppose that I dropped a shell of matter onto a black hole. What would happen? Let's look at that one. So in this case, the red grid is maybe the black hole that you saw in the previous animation. The white grid is a shell of matter which is falling onto the pre-existing black hole. And I've arranged it so that the mass of the shell equals the mass of the black hole. Now, the size of a black hole is proportional to its mass. So if the shell and the black hole have the same mass, that means the black hole should double in size, and therefore its horizon size should double in size. Let's see what happens. Indeed, the underlying black hole seems to expand to meet the collapsing shell. Why does this happen? It's gravitational lensing. The massive shell gravitationally lenses the image of the black hole beneath it. And so the two spheres, their grids of latitude and longitude, seem to merge miraculously, just as they should. I want to show you more about special relativistic beaming. In order to do that, I'm going to stop the clock and get rid of the black hole. There it's gone. I'm going to bring up in its place an object with the same size as the black hole. I'm going to go some distance away, and there we go. If the black hole was there, it would look like this. If I remove the black hole, it looks like this. That has the same, this is a sphere with the same size as the black hole. You can see that the lensing of the black hole by itself causes it to appear larger than the unlensed sphere of the same size. I want to show you what relativistic aberration looks like. And I can see the center of the Milky Way. And I'm prejudiced, I'm a northerner. So I'm going to take the center of the Milky Way, which is right there, and place the sphere right beside it. And I'm going to accelerate towards the center of the Milky Way. You notice that the clock is not moving. I'm not in flight mode. All I'm going to do is accelerate. I'm going to change my velocity, and we're not going to move. All that's happening here is we're changing our velocity through the scene. You see a number of effects. The view ahead appears blue shifted and contracted, shrunk, whereas the view behind appears redshifted and expanded. These are all aspects of relativistic aberration. Let me turn on the clock on flight mode, and let's go by this sphere painted with lines of latitude and longitude. I'll stop it right there. You can see that it looks like a sphere. Its outline is spherical. Prior to 1959, it had been widely thought that when you move through a scene at close to the speed of light, you would see the scene Lorentz contracted. And then in 1959, independently, Roger Penrose and James Terrell pointed out that no, the light travel time plays an important role, modulates the Lorentz contraction, and it causes the appearance of a scene to be conformally transformed. Conformally means angle preserving. You can see the lines of latitude and longitude on the surface of the sphere remain at 90 degrees, a conformal transformation. And the outline of the sphere remains spherical. Let it keep going. As we pass by the object, let me speed it up a little bit, near the speed of light, some good fraction of the speed of light, it's now receding from us, slower and larger. Let me change. I'm going to change from going away from the black hole, away from the sphere towards it. Just press a little button and it's going to pass by us again. It's coming towards us. Camera is tied to the black hole, recedes away from us. Let me talk about the rules of four-dimensional perspective. As an entry, I'll remind you of the rules of three-dimensional perspective, which began to be understood in the 15th century. This is a sketch by Leonardo da Vinci as an apprentice in Florence around 1481. This is a study for his picture of the Adoration of the Magi. In three-dimensional perspective, two ideas are fundamental. A straight line in three dimensions remains a straight line in perspective, and parallel lines meet at a vanishing point. In Da Vinci's image, you can see the vanishing point of the tiled floor, and you can see the straight parallel lines emerging from the vanishing point. Da Vinci used this image to construct a picture which gave the impression of true three-dimensionality. The rules of four-dimensional perspective are similarly straightforward to understand even without the benefit of mathematics. This image on the left shows an observer at the center of a celestial sphere. I've painted stars on the surface of the celestial sphere. The arrows pointing from the stars towards the observer represent light rays or photons, which go from the star to the observer. Suppose the observer is moving through the scene at some fraction of the speed of light, here 80% of the speed of light. How does the view become distorted? The answer is you take the celestial sphere and you stretch it out by a Lorentz factor gamma, gamma equals 1 over the square root of 1 minus b squared over c squared, into a celestial ellipsoid. The stars on the surface of that celestial ellipsoid stretch out with the ellipsoid. Meanwhile, one displaces the observer to a focus of the ellipse, away from the center to a focus. In the transformed scene, you notice that the arrows of the photons have become longer ahead and shorter behind. The length of the arrows is proportional to the energy or frequency of the photons. So the photons ahead appear blue shifted, higher frequency, higher energy, while the photons behind appear red shifted, lower energy, lower frequency. In addition to the changes in the frequency, you can see that the view ahead is squashed. What was 90 degrees between the stars on the scene at rest, the observer moving through it at 80% of the speed of light sees the stars at less than 90 degrees ahead. Stars behind appear expanded. So these are the rules of four-dimensional perspective. The change from going away from the sphere to going towards it, and pose the question, how does the black hole flight simulator, how does it realize Lorentz transformations? Well, it's exactly as I showed in those images. Let me displace us away from the focus of from the observer's place. You can see that the image of the distant galaxy is painted on a celestial ellipsoid. We, the observer, would normally be at the focus of the ellipsoid, but here I've given us a godlike focus. You can see the probe, which is coming towards us. Let's look at it. Let's turn on the black hole flight simulator. And you can see the probe approaching us at the focus. The camera follows the probe and it becomes redshifted. So you can see the black hole flight simulator uses precisely this picture of how a scene is Lorentz transformed. I want to explain to you some of the mathematics behind this. This is a conference on the geometric algebra, and indeed it's the geometric algebra in which the black hole flight simulator implements Lorentz transformations. Let me remind you first about ordinary three-dimensional rotations. Game programmers know that quaternions are the fastest and most efficient way to encode spatial rotations. They compose, you can interpolate them, you can spline them. The algebra is very elegant, makes it rapid. Aficionados of the geometric algebra will know that quaternions are simply the even part of the three-dimensional geometric algebra. A quaternion is invented by William Rowan Hamilton in 1843, is a kind of souped-up complex number with three anti-commuting imaginaries, I, J, and K. A can be represented by a four-component object with W, the real part, X, Y, and Z, the quaternionic imaginary parts. A rotation is encoded by a kind of quaternion, a spatial rotor, which is a quaternion of unit modulus, unit length. A rotor is the exponential of a bivector. A bivector is a quaternion with just a three-component quaternionic part, not a real part. So a rotation in three dimensions can be represented by this angle, three-dimensional angle representing rotations about the three possible axes, X, Y, and Z. As always, a multivector, whether even or odd, in the geometric algebra transforms in this characteristic fashion. Now, one of the things one has to deal with in a three-dimensional scene are position vectors of objects in the scene. A position vector is a vector or multivector of grade 1. It's not an even, it's not a bivector, it's not a quaternion. Nevertheless, the object of a position in three-dimensional scene can be encoded as a quaternion because it happens to be that in 3 dimensions, a vector equals the pseudoscalar multiplied by a vector. So a position vector transforms in the same way as a bivector, and it has the same number of components as a bivector, and therefore a 3D position can be encoded as a quaternion. This is part of the magic of quaternions as a way to represent scenes in 3 dimensions. Complex quaternions have the same kind of benefits for Lorentz transformations. In relativity, space-time becomes 1 dimensions, 3 plus 1 dimensional. And rotations of space-time, also known as Lorentz transformations, are encoded as complex quaternions. A complex quaternion is a complex sum of 2 real quaternions, a real one and an imaginary one, multiplied by yet another imaginary, I, which happens to be the pseudoscalar of the 3 plus 1 dimensional geometric algebra. A computer person can encode a complex quaternion as a combination of two quaternions, a pair of quaternions, a real one and an imaginary one. The bivectors of the 3 + 1 dimensional geometric algebra, there are 6 of them, consisting of 3 spatial rotations, the I, J, and K imaginaries, and 3 Lorentz boosts, which are the pseudoscalar multiplied by the 3 imaginaries. The 3 Lorentz boosts correspond to changes of velocity in each of the 3 dimensions, x, y, and z. They're rotations between a spatial axis and the time axis. As usual in a geometric algebra, multivectors, even or odd, transform in the usual way with rotors. And as in the 3-dimensional geometric algebra, in 3 + 1 dimensions, a Lorentz rotor is a quaternion of unit modulus. It is the exponential of a bivector. There are 6 bivectors, 6 basis bivectors. So the angle in relativity is a 6-dimensional angle with real parts and imaginary parts. The real parts encode a spatial rotation. The imaginary part encodes a Lorentz boost in each of the 3 directions. As in 3 dimensions, one has the problem of representing position vectors of objects in a relativistic scene. In relativity, in 3 + 1 dimensions, an odd multivector can be written uniquely as a product of a time vector and an even vector, a quaternion. And in that way, an odd multivector, a position vector, can be encoded as a complex quaternion. It's an odd multivector, so it transforms as in the usual way, which looks like that. But commuting the time vector through the rotor converts the rotor to its complex conjugate with respect to the pseudoscalar. So the net result is that an odd multivector in 3 + 1 dimensions transforms a little bit differently than an ordinary multivector. Now, positions in a relativistic scene are light rays. Remember this picture? The position vectors of stars, an observer sees them along a light ray. And a light ray is a null 4-vector, a 4-vector that moves at the speed of light. In relativity, null 4 vectors are represented by a magnitude multiplied by 1 plus this pseudoscalar multiplied by a unit vector. So they take the form of a complex quaternion. The bottom line of this is that complex quaternions are just as powerful in relativistic simulation as ordinary quaternions are in 3D visualization. We've got one more thing to do. I'm going to bring us back to where we were, remove our velocity, and bring back the black hole, wherever it's gone. There it is. I want to take you into the black hole. So once again, I'm going to take us into an unstable circular orbit. Let's put this in the right form, mix it up a little bit. There we go. Into an unstable orbit around the black hole. A convenient place. Let's just mix it up a little bit. A convenient place from which to fall in. I'm going to get rid of these other probes. And I'm going to do, let me just, whoa. Let me halt it for a little while. Kind of gets confusing. Change the texture to make it a little bit nicer. There we go. In order to fall in, let's get the clock going again. In order to fall in, I need to lose some angular momentum. That means I have to do a little fire on my retrothruster. So there it is. And now we're going to fall in. You can see how close we are to the horizon from the map on the left. As we approach the horizon, I'm going to slow it down. And whoa, what just happened? Let me stop it just there. We're now inside the event horizon. What has happened? That white grid, bluish white grid above us, is the event horizon. It seems that the horizon has split into two. You might have thought that falling through the horizon, we'd fall through the red grid. But no, that didn't happen. Instead, the horizon split into two. And the true horizon, the event horizon, forms this kind of igloo over our head. Well, what's going on here? When I first did these visualizations many years ago, this puzzled me for quite a long time. Remember that when you're inside the horizon of a black hole, space is falling faster than the speed of light. So whichever direction you look at, you're looking from light that originated from outside of you. So if you look up, you see the outside world and you see the event horizon. But if you look down, you also are looking outwards and you're seeing the event horizon. Actually, what you're looking at in this red grid isn't really the event horizon at all. It is the redshifting dimming surface of the star that collapsed long ago. When we fall through the horizon, we don't catch up with the star that collapsed long ago. It's already gone to the singularity, already collapsed. And we see it still redshifting and dimming away, even though we ourselves are now inside the event horizon. Let me back up. Let's fall through this horizon again. Imagine that we're falling feet first. We've just fallen through the horizon right now. The horizon is forming we're inside the horizon. It forms this canopy over our head. If we fall feet first, we see our feet still below us. You can imagine that at the moment your feet fell through the horizon, they would emit light upwards at the horizon. And because the light is emitted upwards at the horizon, it just hangs there forever, going at the speed of light through space that's falling at the speed of light. Meanwhile, we are falling towards the horizon and we catch up with the image of our feet below us. We catch up with the image of our feet, but we do not catch up with our feet. Our feet still appear below us. And the same is true for the redshifting star. It's still below us. Our feet are below us, and the redshifting dimming star is still below us. There are a number of myths about what happens when you fall inside the horizon of a black hole. One is that you're engulfed in blackness. Plainly, that isn't true. We've fallen through the horizon. Light can fall through the horizon. We can see the light that's fallen through the horizon. People outside can't see us inside the horizon, but we can see them. A second myth is that time slows down inside the horizon. I'm actually slowing down the clock because everything happens in a huge rush as we approach the singularity. But no, for us, time always goes by at 1 second per second, even though we're well inside the black hole near the singularity. Another myth is that you never reach the horizon because it's infinitely redshifted. Again, no, we fall through the horizon and we reach the singularity in a finite time. We're going to hit the singularity any moment. Ouch. There it is. We've reached the singularity. I've stopped the clock. General relativity doesn't know how to proceed past this point. The curvature has become infinite. The tidal force has become infinite. We are dead. The best we can do is say, from general relativity's point of view, time has come to an end. Presumably in quantum gravity, something continues. Exactly what that is remains a matter of debate. Luckily, we have a back button. I push the back button, we can go back in time in the black hole flight simulator. Of course, you can't do that in reality. Let's look around. You never get to see the singularity. It looks like a flat plane. It looks blue shifted ahead and red shifted behind. Let me remove my angular motion. Let's imagine that instead of falling in with some angular motion, we fell in radially. This is what it would look like. Look around, looks like a flat plane. Look up, it looks red shifted. Look around the equator, it looks blue shifted. Why does it look like this? It's because the diverging tidal forces is causing the scene to be tidally aberrated, so it's red shifted above and blue shifted towards the side. Something that we can't do, but I can do in the black hole flight simulators, take you on a tour around the singular surface. It looks like a flat plane indeed. And it has the geometry of a sphere, a spherical topology. Looks like a flat plane. Is it true? Actually, it really is a surface. One of the most widely quoted myths is that the singularity at the center of a black hole is a point. This sphere, this red line, represents the horizon of a spherical black hole, a Schwarzschild black hole. And I want you to imagine two people, a blue person who falls in radially, free falls, reaching the singularity at the center. Meanwhile, a purple person also free falls radially along a different angular position. You can imagine the two people do their best to try to fall in at the same time. And the question is, do the two people meet each other at the central singularity? Do they get to shake hands? Remember that inside a black hole, space falls faster than the speed of light. So whatever direction it's pointed, inside, inwards or outwards, light is always forced to move inwards. And there is light that has the maximum possible angular motion. The boundary of this gray cardioid region, it's a mathematical cardioid, represents light with a maximum possible angular motion. It reaches the singularity just at the point where the blue person can see it. Everything in the yellow regime is visible to the blue person. Photons can come in and hit the blue person just before they reach the singularity and are visible. But everything in the gray cardioid is invisible to the blue person. Light rays from the gray region would have to move faster than the speed of light to hit the blue person before they hit the singularity. The result is that the blue and the purple person, far from hitting each other at the singularity, already lose causal contact, well away from the singularity. The last that the blue person sees of the purple person is here. And likewise, the last that the purple person sees of the blue person is here, well away. So when the blue and purple person fall to the singularity, they fall to two causally separated points. The singularity is a surface, a causally separated surface, and not a point. You might object and say, well, the angular distance between the purple person and the blue person goes to zero at the singularity. You can try and draw a little arc between the two, and the length of that arc goes to zero at the singularity, and that is true. However, being spatially close, counterintuitively in general relativity, does not imply being causally close. The shortest causal path between the blue person and the purple person just hitting the singularity is this red line. You can imagine that this is a pair of photons created at the red star. One photon is sent in one direction, just hits the blue person as they hit the singularity, and the other photon goes off in the opposite direction, just hitting the purple person as they hit the singularity. The bottom line that I conclude is that the singularity is a causally separated surface and not a point, which probably has profound implications in quantum gravity. I'm done, so thank you very much. You're very welcome to visit my website or send me an email.